right? Chapter 10, gases. Gas is one of the physical states of matter, right? You have a solid, liquid, and a gas. And a gas here, you can see that the particles, they are further each other, right? Okay. So the gas properties. So gases, they are mainly composed mainly of non-metallic elements, right? You can see here, hydrogen, nitrogen, oxygen, fluorine, chlorine, they're all gases, and they are non-metal, right? Non-metallic. And here, the noble gases, right? And the gases expand to fill the container. Expand to fill the containers. So the gases, for example, if you have a gas that initially in a tank, like 100 milliliters tank, and you transfer this gas to another tank, like a larger one, for example, 500 milliliters, right? The same gas that was here initially, if you transfer to another container, to a larger container, the gas will expand to fill the other container here. So it says, the gases expand to fill the containers. Because gases, they have no fixed volume and nor fixed shape. So no fixed volume, right? And no fixed shape. So they get the volume and the shape of the container. And the gas, they are highly compressible. So you can press the gases, you can compress, and you also can expand, right? And the gas, they have extremely low density. Extremely low densities. And when you have two or more gases, they form a homogeneous mixture. So when you have two or more gases, right? They will form a homogeneous mixture. Homogeneous mixture. Right? Okay, so gases, we'll be working with some parameters here, some variables like temperature, right? Volume, mole numbers, and pressure. For temperature, we'll be working in Kelvin. So the question, sometimes the question we give you the temperature in Celsius, so you need to convert from Celsius to Kelvin, right? So to convert from Celsius to Kelvin, you get the temperature in Celsius and add 273 to convert to Kelvin, right? Volume will be in liters. So 1 liter has 1,000 milliliter. So sometimes you need to do the conversion from milliliters to liters, right? And then amount of gas be usually expressed as number of moles, right? Moles. And how can you calculate moles? So one way is mass, right? Take divided by molar mass. All right? Okay. So temperature should be in Kelvin, volume in liters, amount of gas, moles, and pressure. We have different units for pressure, right? Atmospheric pressure. So pressure is the amount of force applied to an area. Applied to pressure is equal force divided by area here. And atmospheric pressure is the weight of air per unit of area, right? So units of pressure have here Pascal, bar, millimeters of mercury or torr, and ATM, atmosphere. So we'll be working using in ATM. So if the question gives different unit, we need to convert from that unit to ATM. So the conversion between units of pressure. 1 ATM is equal to 760 torr, that is equal to 760 millimeters of mercury, right? That is equal to 101.325 kilopascal. That's equal to 1.10325 bars. Now, but sometimes you need to do the conversion, right? So there's a conversion between the units here. So, for example, how do the conversion from ATM into torr, right? So how do the conversion here? You're gonna write first what was given, 0.357 ATM to torr, right? So to the conversion here, which one stays on the bottom? ATM or torr? So the unit given stays on the bottom, right? And the wanted unit stays on the top. So what one here? From ATM into torr, so let's use this equivalence here, right? We'll know at one ATM, at each one ATM, you have 760 torr. Then you can do the calculation here, right? Cancel out ATM with ATM, your answer will be in torrs, right? And here is the opposite. Here, this example shows from torr to ATM. So start with what was given, right? 6.6 times 10 to the minus 2 torr multiply by. So now it's from torr to ATM. Which one stays on the bottom? Now you want to cancel out torr, right? So let's write torr on the bottom here. So you know that 1 ATM is equal to 760 torr, right? Then now we can calculate it here. So from torr to ATM, you divide by 760, right? Cancel out the unit here. Cancel out torr with torr, and you have the answer here in ATM. And the first example here, from ATM into torr, you multiply by 760. And from torr to ATM, you divide by 760. Then part 2, gas law. Observing the behavior of gases through properties that describe their states under certain conditions. So here, it's referring to ideal gases. So ideal gases are gases at high temperature and low pressure. So ideal gases, we consider ideal gases the gases that when they are in high temperature and low pressure, because at these conditions, the gases behave ideally. So, but actually, ideal gases, they actually do not exist really. But we assume that they behave ideally at high temperature and low pressure, right? So ideal gases, gases that behave ideally at these conditions. So now that we have talked about pressure, volume, temperature, and mole numbers in relation to a gas, how do all these properties relate to one another? The first law here, Dalton's law, Dalton's law of partial pressure. So if you have two gases, for example here, right, the gas 1 with this gas 2 here, they are putting together in the same container here, right? So if two gases that don't react are combined in a container, they act as if they are alone in a container. So here, look, gas 1, gas 2, right? They are combined here, but they are not reacting with one another. They behave like each one was alone in the container. So they will not react. In the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. So like here, for example, if the pressure for gas 1 was like 3 atm, and the pressure for gas 2 was like 2 atm, what will gonna be the pressure when you add up the two gases here, the two gases, the final pressure will be, right? The total pressure will be 5 atm. So the equation for partial pressure for the total pressure is the sum of the pressure of each gas. And then pressure in mole fraction. Because each gas in a mixture acts as if it is alone, we can relate amount in a mixture of partial pressure. So I was seeing here, pressure, the pressure of each individual gas. Like, let me say that you don't have the individual pressure. The question gives the final pressure, the total pressure here. The question asks, what's the pressure for gas 1 and what's the pressure for gas 2? How can you find out here? Using this formula here. The pressure, for example here, the pressure of gas 1 is equal to the mole numbers of gas 1 divided by the total moles of both gas 1 and gas 2 times the total pressure. So this portion here, actually, in 1 divided by T is the mole fraction. Mole fraction is the moles, right, of one component divided by the total here. The total moles. And this formula here can use X. X is for mole fraction. So the pressure of each individual gas will be the mole fraction of each gas multiplied by the total pressure. This is Dalton Law's partial pressure. It's related when you have a mixture. The gas did not react, and they act as it was alone. And the total pressure is the sum of each individual pressure here. The next law is about Boyle's law. Boyle's law says that at constant temperature, the volume of a fixed quantity of gas is inversely proportional to the pressure. So what it says here, what says? Constant temperature, right? So temperature here is not changing. And the volume of a fixed quantity is amount of, right? They're going to be not moles, the same. It says that the volume of gas is inversely proportional to the pressure. That it means when pressure increases, volume decreases, right? And what is the equation for Boyle's law? So the equation for Boyle's law is V1 equal P2 V2, right? So for example, let's say if you have a condition here, the initial pressure of the gas was 1 atm, and the P2, the final pressure, was 2 atm here, right? This formula here should, okay, to calculate, if you have the two conditions here, right? The initial pressure, initial volume, and the final pressure and the final volume here. So we have these parameters here, and we are going to identify, okay, what would be the final volume if the pressure changed from 1 to 2, right? So let's plug the numbers in this formula here. So P1 is 1 atm, right? Times V1, 3 liters. Oops. P2 is 2 atm here, right? You choose the 2 atm, but you could choose in another number just to give an example how to calculate the final volume using Boyle's law. So P2 is 2 atm here times V2, right? So your goal here is to find what's the final volume. So the final volume here will be what? So we're gonna multiply here, right? 1 atm times 3 liters divided by 2 atm. So we're gonna cancel out atm of atm. You know that your final volume will be 3 divided by 2, right? It will be 1.5 liters. So how will be the graph here for Boyle's law, right? So let's get the points here. So when the pressure was 1, right? Let's say 1 here. The volume was 3. So let's say that 3 was here, right? And when the pressure changed to 2 atm, oops, I put the back order, right? So let me redo here. So let's say here, when the volume was 3 liters, right? And the initial pressure was 1, so should be here. So what happened, and then the final pressure here was 2 atm. So the final volume changed to 1.5, right? So here's for atm and here's for volume. What's happening here, right? So Boyle's law is inversion, the volume of gas, right, is inversely proportional to the pressure. So the graph for Boyle's law will be going down like this, right? Okay. So next law is, let's write it here, final volume, 1.5 liters. So, by the way, significant figures, right? Let's use here, 3 significant figures. Okay. Then Charles' law says that at constant pressure, the temperature of a fixed quantity of a gas is directly proportional to the volume. That means when volume increases, temperature also increases. And what's the equation for Charles' law? So for Charles' law, the equation will be V1, T1, right? V1 divided by T1 equal V2 divided by T2. So for Charles' law, you just need to know about the volume and temperature here, right? So for example, let's make solve this problem here. So for Charles' law, the pressure is constant, right? And the mole number is also constant. The only thing that is changed in Charles' law is volume and temperature. So let's say if you have a condition here, the initial volume of your gas is 3 liters. Let's say, and the final volume changed to, let's say, 5 liters. And if the initial temperature was 298 Kelvin, what will gonna be the final temperature here? We are going to plug here, right? So V1, 3 liters, divide by T1, 298 Kelvin, equal to final volume, 5 liters, divided by the final temperature here, right? So I just choose 5, he just choose an example, but you could choose any another number, right? Just to figure out what's gonna be the final in these conditions here. So solving 42, right? What's gonna be here? We're gonna have 5 liters, right? Multiplied by 298 Kelvin, divided by 3 liters here. Then we're gonna calculate here, multiply and divide by, right? Cancel out liters with liters. So you know here what gonna be your temperature in Kelvin, right? Okay. And for Charles' law, the graph will increase so you know that in Charles' law, volume and temperature, they are directly proportional. That it means both will increase, right? So the graph for Charles' law is going to be like this, going up, right? Because if you calculate this, you expect a higher temperature, right? Here. 5 times 298 divided by 3 would be about 197 Kelvin. Here, right? Okay, so let's see the next one here. So Boyle's law, right? P1, V1 equal P2, V2. Charles' law, V1 divided by T1 equal V2 divided by T2. So for Charles' law, is inversely proportional, right? Volume and pressure. And for Charles' law, temperature and volume directly proportional. The next law is about Gay-Lussac's law. Gay-Lussac's law says that at a constant volume, the temperature of a fixed quantity of gas is directly proportional to the pressure. What that means here. So the volume, right, is constant. Okay, volume 33 is the same, right? What else the same? Fixed quantity. So mole is also not changed. What's changing here is change pressure and temperature here. And Gay-Lussac's law says that pressure and temperature is directly proportional. That it means when pressure increases, right, temperature also increases. So, and what's the equation for Gay-Lussac's law? P1 to 1 equal P2 to 2 here. Right? So, and that makes sense, right? Because if you apply a pressure in a system, right, the molecules, the gas will have more contact with each other, right? So you also will warm up. And for example, what's gonna be the final temperature here, right? If you have a condition, the initial condition for the gas was 1 atm, and the temperature was 298. So let's say what's gonna be the final temperature if the initial pressure changing, or is initially 1 and changed to 2 atm, right? So let's see here. Then I'm gonna plug here the same thing. P1, 1 atm. T1, right, divided by T1 is 298 Kelvin, equal to final pressure. We use here 2 atm as an example, right? Divided by what's gonna be the final temperature here, right? So we're gonna do the math here, and to find the final temperature, right, should be like 2 atm times 298 Kelvin, right? Divided by 1 atm. I'm just writing here just to show the units cancel out, right? So cancel out atm with atm. Your final answer should be in Kelvin, right? So you can see here, when we increase the pressure, the temperature also increases, right? So you know 2 times 298 would be 596 Kelvin. 596 Kelvin here. So, and if you plug these numbers here, you figure out that the graph for Gay-Lussac's law is also going up here, right? So right now what you saw, the only going down is related to Boyle's law, right? All other ones, the graph is going up. Because all other ones, they are directly proportional. The next one here, you have Avogadro's law. So it says that at constant pressure and temperature, so now you have a constant pressure, right? And constant temperature here, the volume of a gas is directly proportional to the moles of a gas. At standard temperature and pressure, 1 mole of any gas is 22.4 liters. Standard temperature and pressure here, STP, right, is the temperature at 273 Kelvin and 1 atm. This These here are the conditions STP, standard temperature and pressure, right? So you can see here that the temperature here, they are not at standard condition, right? The pressure, yes, but not the temperature here. So we need to calculate here to find what will be this math here. So Avogadro's law, when volume increases, moles also increase here, right? And what's the equation for Avogadro's law? Initial volume divided by initial mole numbers, right, is equal to final volume divided by final mole numbers. All right? So what you have here? What you have here? So we know when the volume increases, mole numbers should increase, right? So let's use an example here. If the initial volume is 3 and the final volume is like 4 liters, and let's say the initial mole numbers was like 1 mole, what are going to be the final mole numbers here? So we're going to plug everything to solve for the unknown. Right now, the only unknown here is mole numbers, right? So let's plug the numbers here. U1, 3 liters. N1, 1 mole, right? Equal to final volume per liter divided by N2 that you don't know yet, right? Let's go here, N2. So we're going to solve, right, about the same way. You are going to solve it for the unknown. The only known here is N2, right? So it would be what? N2 is equal to 4 liters, right? Times 1 mole divided by 3 liters here. When I cancel out liters with liters, your ink should be in mole here, right? So then do these calculations here. So you should get 1.33. Right? And it's what? What is happening here? When the volume changes from 3 to 4, the mole numbers change from 1 to 1.33 moles, right? So you can see here that volume in mole numbers is directly proportional, right? If you are at constant pressure and constant temperature here. So this graph here for Avogadro's law, you also expect to be going up in here, right?